Here we are, section 12.1, talking about maxima and minima. So the maximum, the highest value, the minimum, the lowest y value. So we record the x values where those extreme y values, either maximum or minimums, occur. So let's look at some examples and sort of how we use calculus to figure these out. A lot of this can be done by actually just looking at the graph, but we will use calculus in many different ways, a few different ways, to take these. So with this graph here, we can see there's some high points, some maximums here. So we could call these local or regional neighborhood maximums, right? And actually there's a particular point that is the maximum. There is a maximum here at the endpoint. So there's two endpoints on here, as they've got them labeled here, and one is it's a local maximum. This one over here, the A, would be a local minimum. And then there's also a local minimum here at this point. It's a very specialized type because you can actually you can't take the derivative there, but everywhere else, these two maximums we can take the derivative at, and down here we've got a minimum we can take the derivative. You'll see that when you've got these what they call stationary points, because when you take the derivative it's zero, so that's a stationary, it's constant, right? The derivative is constant at those points, two maximum and one minimum. So those are places where the first derivative equals zero. So that's one test we're going to use to help us find maximum and minimums, is we'll look for the first derivative where it's zero. Now, endpoints, you can't take the derivatives, but you can, usually they give you a value of what those endpoints are, the x values. You plug those in the function, and then you can find what those y values are as far as the actual values of the minimums and maximums. Okay, so we have relative minimums and maximums, which mean that it's just the high point or the low point in that area. And then for the function as a whole, there would be one value that could be the absolute maximum or absolute minimum. And in this one, it looks like it's got that this stationary point here would be our absolute minimum. Nothing else is lower than this point here. Okay, if I've got that right. And this endpoint here would be our absolute maximum because there are no y values higher than this endpoint. Okay. So those are the concepts we've got going with this. We will use the first derivative test, and it kind of helps us in two ways. First of all, where the first derivative is equal to zero, that identifies a critical point, which we call C. C for critical, right? So you'll some of these questions will look for critical points, for the most part, we can just say that's where the first derivative is zero. Now, there's examples of critical points where that doesn't happen, but for the most part, let's proceed with that. So what we do is, if we've got a point that is a critical point, we know its first derivative, the tangent line at that point, is zero. Now, there's two ways this can happen. We could have a minimum at that point. Comes down like that, which means that the first derivative is negative because it's decreasing here. It's equal to a negative value, and then it becomes positive because the slope is going up. So it's a positive slope. So the first derivative goes from negative to positive. So you check, you find your critical point where the derivative equals zero, and then you look if it's going from, if on the left it's negative and on the right it's positive, we know we've got a minimum. Let's see, that's this one here. Negative to the left, positive to the right. Then we've got a minimum. if instead of that, we have something that goes, and again, sometimes we find these points, if we don't look at the graph, we don't know what it looks like. We've got the first derivative being positive. Excuse me. First derivative being positive and then being negative. See, this is why we have our social distancing. I've got bad allergies, and that's what I haven't had a fever, so I'm pretty sure I'm going to be okay, but just get over these allergies. And then it's negative, so positive and negative. Notice it will give us a maximum. So that's this first one here. And then if it's the same sign on both sides, then it's neither maximum or minimum. And sometimes what that does is what we've got is something that kind of flattens out like this, and it's still increasing on both sides. But it's possible we could have like an inflection point or something. We'll talk about those later. But that's also a possibility, is that just because the first derivative is 0, it might not always be, it could be something like this, okay? So we got to check it. And by checking it, if it's, again, this side, the derivative would be positive, and it would be positive on this side too. So no sign change. And yet right here, I think we would get a 0 first derivative. Okay, so let's look at some examples. And again, if you've got a function that's given and you can graph it, that's one of the best ways to take a look at it. So let's see, let's go with green. So the function, it's got two endpoints at -3 and +3. So those I'm going to put solid dots there. Those are endpoints. F has a relative minimum at which one? A relative minimum. Well, these are absolute minimums down here. So these are the lowest it'll go. But you can see a low point here. So graphically being able to recognize that that's at x equals 0. F has an absolute maximum. So the highest point actually is going to be right here. Now the value is 1.5, but where's it happening? Actually, it happens at 2 places. Notice the value itself is the same, 1.5, but it happens at both -1 and 1. So that can happen. There are 2 points where we have the absolute maximum, but the value of the absolute maximum can only be one value. You can only have one maximum, because if you had 2, one would be bigger than the other, and that you can't have 2. You can't. It doesn't work. Okay. F has an absolute minimum. Well, there's actually, again, 2 places where there's absolute minimum because it's the same value. The minimum itself is a y value of -3. Where it happens is when x is -3 and where x is +3. And +3. F prime is 0 at which x values? Well, everywhere we have these kind of, that we have a horizontal tangent line here, here, and here. So x equals -1, x equals 0, and x equals 1. F prime is positive on the interval. So where is it increasing? So the slope of the tangent line would be positive here. So from -3 to 1, we've got positive here. It decreases here, but then from here to here, so from 0 to 1, it's back to increasing, and then it's decreasing. So that would be negative. So F prime is positive on the 2 green intervals. So that would be -3, and it's a closed interval until we get to -1. Now, -1 is an open interval because the point itself at -1 is neither increasing nor decreasing. And then we've got another interval here from 0 to 1. And again, those are both open intervals that way. Where is it negative? Let's go ahead and change to blue. Well, it's negative. It's decreasing from here to here. So there's our decreasing part. And then from here down to 3. So this part, these are the places where f prime is negative. Okay, so we start at -1 and we go to 0. And then we start at +1 and we go all the way to +3. And in this case, 3 is a closed order where the others are open intervals. Okay, so that's how we look at a graph. And they're using the and instead of the union. Either one would work. They didn't put endpoints. Let's see. I guess, yeah, I'll back up on. You really can't take the derivative at the endpoints. So, okay, I'll go with them. Let's back this up. Let's go ahead and erase those. Because we can't take the interval at the endpoints. There we go. Always good to check. Okay. Looks like everything else we're right on track. Okay. So let's take a look at 5, another graph. Fewer questions. So the graph of a function f of x is f prime, the first derivative is 0 at what places? Well, everywhere we get a horizontal tangent line, it will be. Now here's a place where I think we're going to see that it's actually going to be 0 here, but it's actually an inflection point. So we know it's at -2 and +2, and because of this change of concavity here, we'll talk about that a little bit later, but the derivative itself, notice we're decreasing, 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 and still decreasing. I'm going to put it out here, but maybe. So f has a relative max at, now notice this arrow's going up, so it's not absolute, but it's definitely a relative maximum here at -2. So notice the derivative will be positive on one side, negative on the other. First derivative, right? Positive to negative. And then we have a relative minimum here at x equals 2. First derivative would be negative, followed by positive on the other side. Negative, positive, and this one is positive, negative. Okay. Not sure about that 0, but I think there's a 0 there. Yeah, they got it. I know the second derivative, we get that a little bit later. Second derivative test is definitely 0 here. That identifies the inflection point. However, the first derivative is often 0 too. If the first derivative is 0, certainly the second derivative is 0, because the derivative of 0 is 0. Okay, so that's that one. So now we're asked to find all critical points of this function. Use the first derivative test to determine whether f has a relative minimum, a relative maximum, or neither at the critical point. So let's see if we could do this first with using the derivative. Again, on a test question, I would go ahead and just graph it to see what it looks like, but I want to see, let's try this sort of old school way just by taking the first derivative. So we'll take the first derivative. Derivative of x is 1. Derivative of natural log of x, so we've got this constant multiplier, is going to be 2 over x, right? Derivative of natural log of x is 1 over x. And x is not equal to 0, so that allows this to happen. So we want to find out where this function equals 0. That'll get us our critical points. So I'm going to add 2 over x to both sides. Multiply both sides by x. And that gives us 2 equals 1x or x, right? So 2 is a critical point because it's the place where the first derivative equals 0. And the way we've gone about solving it, it's the only place. Now, what we want to do is to find out whether it's a relative minimum or maximum using the first derivative test. So we take this first derivative. Now, if you plug in 0 here, you get 2 over 2, which is 1. 1 minus 1 is 0. So what you want to do is plug in values on either side. How about x equals 1? And you could go with x equals 3, but I'm going to go with x equals 4. I don't know. I guess 3 is as good as 4. Yeah, why not? 4 is not good. 4 would give us a half. 3 gives us 2/3, but that's okay. Okay, so the derivative when x is 1, and remember that's to the left of 2, right? We're going to graph this in just a moment. So here's 2. So we know we've got a critical point here somewhere. So we're looking at 1 and 3, and we want to see if does it go negative, positive, does it go positive, negative, or neither one of those. Okay, so let's plug in 1. So we get 1 minus 2 over 1. That's equal to 1 minus 2, and that's equal to negative 1. We take the derivative at 3, and you could go with anything you want. 1 minus 2 over 3. Well, 2/3 is less than 1, so that's going to be actually, think of 1 as 3 over 3. That's going to be 1/3, which is a positive value. Okay, so we went negative, positive. Negative, positive means we went down and then back up, so we've got a minimum. Add x equals 2. Okay. To verify this, let's pull out our friendly, let's see, where's my calculator? So we'll use this browser. Let me bring that. Okay, so we're going to graph this, and what we're going to graph is the actual original function, which is y equals x minus 2 natural log of x. And it shows us right away at x equals 2, we do have a relative minimum, and there's this derivative here on the left-hand side would be negative, and the derivative on the right-hand side is positive. Okay, so verified. You probably could have just graphed it and looked at it. That's true, but this is using the calculus. Okay, critical point x equals 2. It has a relative minimum at x equals 2. And then again, you could plug it in and you would get the exact value. This is the actual value of it, which if you multiply that out, you see from the decimals, it's 0.614. Yeah. Okay. Very good. So 7, consider this function. Find all critical points of f, and then find the absolute extrema of f on this interval, -3 to 2. And remember that the endpoints could also be. So we find all the critical points. And how do we do that? Well, we take the derivative of the function, and then we set it equal to 0. So we get 3 times 8 is 24. X squared, 1 comes down, so that's 24, x to the 0, and that's it. So this function, what we do is we set that equal to 0. So I add 24 to both sides. Divide both sides by 24. We get that x squared equals 1. So when I take the square root of both sides, remember when I do this, I get a plus or minus answer. So I get that x equals plus or minus 1. So the critical points, find all critical points, x equals -1 and 1, 2 of them. So now what I can do is I take this original function and I plug in all, so I've got my 2 critical points here and I've got the endpoints. So I'm going to find f of -3, f of -1, f of 1, and f of 2. See which one is the highest or lowest, because that's where they can occur, right? They either occur at the critical points or they occur at the endpoints. And so this one, I'm going to get 8 times -3 cubed minus 24 times -3 plus 12. And again, this I'll get 8 minus 1 cubed minus 24 times -1 plus 12. Here I'll get 8 1 cubed minus 24 times 1 plus 12. And here I'll get 8 times 2 cubed minus 24 times 2 plus 12. Okay, and again, a graphing calculator is a great way to handle all of this. So I just replace this function here with our function 8x to the third minus 24x plus 12. And again, so the interval was from -3. So notice if I go down to -3 is right here. Wow, it's way down there. Really negative. I'm going to have to learn how to have this thing give me a table. That would be, I'll look at that. Most of your graphing calculators can do it pretty quickly. Let's see. No, let's just go ahead and go to here. I would just plug it in your graphing calculator and use the table feature. Otherwise, you have to go through all of this. Okay, so -3 cubed, that's actually 27, and it's -27. So 27 times 8 equals that. We'll put a negative on it. Negative times negative is a positive, so 24. So we're going to add on 24 times 3. And then we're going to add 12. Yeah, it was way down there, -132. do the same thing with 1. It's going to be a little easier. This will be a -1, so we get -8. That's positive 24. So -8 plus 24 is 16. Positive 16 plus 12. 28. For this one, that's going to be a positive 8, and this will be a negative 24, so that's going to give us negative 16 plus 12 is going to give us a -4. And then this one is obviously, well, obviously, I don't know. 2 to the third is 8. 8 times 8, that's 64. This is minus 48 plus 12. So this is going to be, it would be 24, that's 16. 16 keeps coming up. Plus 12, that's 28. So it looks like we've got two places where we've actually got the same absolute maximum. So find the absolute extrema. We get a absolute max at x equals -1 and 2, and that is a y value of 28. And we have an absolute minimum. Notice -4 would be a relative minimum at x equals -3, and that gives us y equals -132. Okay, and you could, again, looking at the graph, you've got that one there, and then this one here is 2. See, there we go, 2 and 28. 2 -1 and 28, and then we've got this one at -4, 1 and -4. So those values are all there. Okay. -3, we get 132. We've got absolute maximums at 2 places, but only 1 value. Critical points -1 and 1. Okay. Just keep moving along. Okay. So now we're given this function. Find any critical points, and then find the absolute max and it should be absolute min of g over this interval. Okay. So first of all, we're going to take the derivative. Now remember, with the chain rule, we take, this is sort of an outside function, so the 2/3 comes down, x minus 2, subtract 1, so 2/3 minus 3/3, that's the way to write 1, so that's going to give us a -1/3, to the -1/3, and then times the derivative of the inside, which is just 1. I'm going to put that just to make sure you do the chain rule, because if it was like 2x, it would be a 2 out there. So anyway, that's what we get, 2/3 x minus 2 to the -1/3. Now there's a problem here, because this negative puts this down into the denominator. So when we go to try to solve this for 0, set it equal to 0, because that's a negative, what we get is we get x minus 2 to the 1/3 down here. Notice we can't plug in 2. 2 would give us, okay, yeah, 2 would give us 0. 0 times 3 is 0. That's undefined. And we really, you could you could try multiplying by the variable, but then that just cancels it out. There are no critical points. You can't get this equal to 0 because you've got multiplication. The only way you could get 2/3, thinking of this as multiplication, this has to be 0. And the only way this part could be 0 is for x to be 2. 2 minus 2 is 0. But because it's a negative exponent now, it's down there. It's there are no critical values. So I'm going to say critical points, none. And then the absolute max and min over this interval from 0 to 5. So since there are no critical points, again, we could graph this to see what it looks like. But what we could do is probably where things are going to occur is at the endpoints. So we look at the function at 0 and now notice this is not the derivative, it's the function value. So we go back to the very original. So we go 0 minus 2 to the 2/3. This is going to be 5 minus 2 to the 2/3. So this is going to be negative 2 to the 2/3, which is going to be a negative number. And this is going to be 3, positive 3 to the 2/3, which also be some decimal value, but it'll be positive. So I'm going to say, I'm going to go out on a limb that this is our minimum, because a negative is smaller than a positive, and this will be our maximum. So we've got to find the absolute max and absolute min. So I don't know, do they want that plugged in? Probably. So we can go with 2, we'll make it negative, and we'll raise it to the 2 divided by 3 power. I don't think I did order of operations on that. So, okay, let me do this again. We're going to do 2 negative. We're going to raise it. We're going to put a parentheses around it. 2 divided by 3. Yeah, because order of operations says to do the exponent before the division, unless you do it this way. And I'm wondering why don't I have, because I am squaring it. I'm squaring it and then taking a third root, or vice versa is really how it happens. So it is positive. That's something I jumped to. It's 1.5. 1.587. Okay, and then now I'll take this one. We'll take 3 and we'll raise it to the, well, not divided. Clear. 3 raised to the 2 divided by 3 power, which is 2. That still looks like I'm right, 2.08. So we've got a max at 5, 2.08, and a minimum at the point 0, and the y value would be 1.581. Critical point x equals 2. What did I do wrong there? Two-thirds. It's a negative 1/3, which means it's in the denominator. At 5, you get your max, get your minimum. If you could plug in 2 and add, I agree it's equal to 0. If I plug in 0, let me just stop this. I'm puzzled here. Now, that's why it's good having this Remember I said graph first. I try to show this. One of the things we're facing here is the reason we get this critical point is the function is defined at 2. I can plug 2 in here. 2 minus 2 is 0, and that is a value. The derivative is not defined at 2. However, I cannot take that derivative, and it'll become clearer as soon as we look at the graph. We see that this is one that gives us a hard, it's kind of this sharp point that we cannot take the derivative at. However, we can see very easily from this that this is a minimum. It's an absolute minimum because it goes up to the left, it goes up to the right. So this is our minimum point. 0 is here. We did get that value, but 5 is going to actually be, when x is 5, 2.08. That's going to be the maximum, the absolute maximum. This would be a relative maximum because in this area it's a maximum. If it's an endpoint, we erase the rest. But this is one with a sharp point, and we would have only known it by graphing it, because the derivative does not exist at this point. Okay, so we're going to come back here and say that after further consultation, we realized none is not it, that it is x equals 2, but we had to go to the graph. And so this is not an absolute minimum. We do have the maximum here, but the minimum is going to be at the point 2, 0. Okay, so look at the graph. Okay, we're going to keep moving here. Now this one we're going to be okay, it's a polynomial, but we will do the same thing. Let's just go ahead and graph it first. It'll help us find these critical points for what x values is the function k increasing, decreasing. The graph will tell us that the best 2, otherwise you have to plug in a lot of values, find any relative and absolute extreme on k on this interval. So, and it's showing us the answers already, so we don't want to see those. 4x to the third minus 24x squared. Let's see. Let's pull this up and make it a little bit minimized so that I can go ahead and enter this here. So y equals 4x raised to the third power minus 24x squared plus 36x, not that x, little x, minus 20. Okay. Let's just make that enlarged. We can see probably 2 right there, a maximum and a minimum. We'll lock those in. So at 1 and negative 1 and 3, we get critical values. Looks like that's going to be about it. 1 and 3. And then we have to check the endpoints. And what was the endpoint that they were using? Any relative or absolute extreme, negative 1 to 5. So from negative 1, way down here, negative 1, negative 84. Graphing calculator, negative 1, negative 84. That's got to be an absolute minimum. And then when we go back to the graph, there's a relative maximum, a relative minimum, but look at what's going to happen is 5 is going to be the endpoint, right? So we're going from -1 to 5. So 560 is going to be our maximum. What x values is the function k? Okay, we come at critical points. Critical points were 1 and 4, or 1 and -4, right? Come back down. Yeah, it's -4. So there's that one there. We lock it in, 1 and -4, and 3 and -20. Critical points. Now when they say critical values, they're looking just for the x value, but a critical point is a coordinate. And then it was what? 3 and -20. Yeah, that's it. Right from there. For what x values is the function k increasing? When is it decreasing? So again, just looking back at the graph, it's increasing here until 1, and then it's increasing again after 3. So from -infinity until 1, we get increasing, and then it increases again from 3 to positive infinity. The place where it's decreasing is in between these two, from 1 to 3. That's the decreasing portion of the graph. So I think we did this all. We were able to do it without calculus. If you'd like, take the derivative of this. 3 times 4 is 12x squared. 2 times 24 is 48x plus 36. You would look for where that equals 0. Notice 12 can factor out of this. So this is, we're going to see 1 and 3 are the values we end up getting. So that gives us x squared minus 4x plus 3 equals 0. So divide both sides by 12, so the 12's gone. And then factor this inside. This is going to be x plus 3, not x plus, because we got a negative in the middle. So it's going to be x minus 3 times x minus 1. So back to the factoring that you would have learned in Math 117. This is why we use it. Again, the graph was very helpful. So x minus 3 equals 0, or x minus 1 equals 0. So this top one gives us x equals 3, and this gives us x equals 1. So there's our 1 and 3, plug them in, and we're good. So critical points, x equals 1 and 3, actually those are critical values. When you call them critical points, you need coordinates. It's increasing from -1, 1, from -1. Oh, because of the, okay, I see what happened. So they implied, or they wanted this interval to apply for b as well, which would have been nice if we put it up here, but that's okay. So we can get the infinities out of there. They're just wanting to use the same interval. And decreasing, again, I was always taught that these should be open intervals here, because at the point of a min or a max, it's actually neither increasing nor decreasing. So I just, while it's okay, this part really should be 1 to 3. It's neither increasing nor decreasing at either 1 or 3. Okay, and again, you could have infinities here. That's how I interpreted it. They don't mention the interval, the restricted interval, until the end. So that's how I would do that. Let's see how we did on everything else. So when we plug in 5, we get 60, and that's an absolute max. We did that all right. Absolute minimum at -1, -84. So those are our endpoints. And then we get relative minimum and max, but notice it didn't ask for those. But yes, we knew these would be places of relative max, a relative min. Oh, it did ask for relative. Okay, so relative max 1, -4. I would have written it this way, and relative min 3, -2. So just make sure when you read a test question, you read it thoroughly. I was focused on the absolute rather than the relatives. Okay, I think I might stop after this one. It's been a long morning of several hours straight doing math, and we'll do one more. I think this is it. Let's see, 10. Oh, we've got a ways to go. So let me keep moving, and if I make too many mistakes, we'll come back. So this function, what we could do again, we could take the derivative, and let's just do that. Derivative of e to the x is e to the x. Derivative of -x is just -1. Okay, so critical points, we set this equal to 0. Add 1 to both sides, you get 1 equals e to the x. Well, that happens whenever x is 0. So if you put in 0 for an exponent, anything to the 0 power is 1. So yes, at x equals 0, we get a critical point. Find any relative and absolute extrema, again, on this interval. And I'm going to look at both of them, relative or absolute. So we look at the two endpoints, plug those into the original, and then we've also got to plug this one because there's x equals 0. There should be a min or a max there. Probably we're subtracting. I'll bet you it's a minimum. So let's look at h of -2, h of 0, and h of 3. So we get e to the -2 minus 2. This gives us e to the 0 minus 0, which equals 1. And this gives us e to the 3 minus 3. Okay, since e is a number that's 2.8, it's almost 3. This is going to be close to in the 20s, -3. So this is going to be a fairly large value. You can actually calculate it out. So let's see, do we have an e here? We have, here we go, e raised to the 3rd is equal to that, 20. Subtract 3, and we get 17.085. I think if I looked at that, you could round that up 1 decimal place, right? Yeah. This is 1, and then this e to the -2, e raised to the 2 minus gives us that, -2 gives us that, -1.86. So I would say we have an absolute minimum at negative 2, negative 1.86. We have an absolute maximum at 3, 17.086. And what's this going to be? So we got a minimum, a maximum. You could take a look at what the derivative is on either side of 0. See, here's this. So if you have a negative here, you're subtracting 1. This will be negative. The derivative will be negative on this side of 0. So let's put in 1. That's makes it 2.78. That's going to be positive. So you're going negative and then positive. This has got to be a relative minimum. Relative minimum at 0, 1. And let's verify that with the graph. That should be exactly what's happening, e to the x minus x. And then we'll look at the answers because I feel pretty confident about what we've done. Y equals e to the x minus x. Yeah, see, we got it. We do get a minimum coming down, going up. What was the other boundary? Was negative 2. Negative 2 gets us about what did I do there? Negative 2. Oh, caught up again. Negative 2. When I plug in, this needs to be negative 2, so that makes it a positive 2. Redo my arithmetic. This is e to the minus 2 plus 2. So this is not an absolute minimum. It would be a relative maximum, right? Relative max. But it's not that. It's negative 2 e to the minus 2. It's definitely time to take a break, but I want to at least get this posted because all the methods are good, and the struggles I'm having with the math, arithmetic, hopefully will be beneficial. I'll do that, and then it's going to be plus 2. It's 2.135. Which again, we're going to see when we go to the graph. $2.135, exactly. And then when we go to 3, it's going to be about here. $17.86. 17.86. So we've got those right. Look at our answers. They left them in their forms. To be able to tell whether it was max or min, though, I needed to kind of convert these over. We've got an absolute minimum at 0, 1. We've got that one. We've got an absolute max here, and then a relative max at that end. There is no relative min, although you could say this is a relative min also. I mean, it is. It's in its neighborhood. It's a minimum. Okay. Very good. Let's look through some true, false, and then I think there's one more question after this. So suppose f of x is continuous everywhere. F has 2 critical points, one here and one there, so negative 1 and 2. So that, and then we're told that the derivative at negative 2 is negative, but it's less than 0. The derivative at 0 is greater than 0. So that's going on either side of 1. So to the left of 1, what we have is we've got the derivative is negative, and then to the right of 1, notice 0, or right of -1, we've got positive. So what we're doing is we're kind of negative and then positive. That's got to be a minimum, right? And then for the derivative at 3, it's negative. So what we've got for 2, again, we can use this middle point here because it's less than 2. So we're going from positive to negative, to negative. So we're going to have a maximum at 2. Relative minimum at 1, -1, relative maximum at 2. Okay, that's what that's all say. F has a relative minimum at -1 because F is decreasing on the left side of x equals -1 and increasing on the right side of -1. That is true. F has a relative maximum at x equals 2 because F is positive on the left side and negative on the right side. That is true. F is decreasing on the interval from -1 to 2. So between -1 and 2, no, it's increasing, right? Because the derivative is positive. This is false. F is decreasing on the interval 2 to infinity. No, because we're told here the derivative is negative, so it's decreasing. Oh wait, that's what I said. F is decreasing on the interval 2 to infinity. Yes, yes. Negative slope, so it's decreasing. So that is true. So true, true, false, true. True, true, false, true. Okay, so that's that one. Not too bad. And then hopefully this one's just as straightforward. So suppose f of x, again, is continuous everywhere, -infinity to infinity, has 2 critical points, one here, so at 0 and 4. And then we're told that the derivative at -1, so that's to the left of this point, so say that's 0, at -1, where our derivative's negative. At +1, it's also negative, so it's negative on this side. And then at the derivative at 5 is positive. So 5 is, here's this point, 5 is positive. So negative, negative, that's inconclusive. It doesn't tell us anything. But negative, so it's coming down and then going up. This is a relative minimum, right? It's got to be a relative minimum. So f has a relative minimum at x equals 0. Again, because it's negative to negative, it's not an extrema, not at 0, because it's negative on both sides, right? We'll get that right. -1 is negative, derivative at 1 is negative. Okay. F has a relative minimum, maximum, such as at 4. At 4, it's got to be a relative minimum. So that's this minimum one, because it goes from negative to positive. F is increasing on the intervals. Okay, so this is telling us negative means it's decreasing, decreasing, keeps decreasing until it gets to 4. 4 is the place where it starts to increase. 4 to infinity, it'll be increasing. And F is decreasing on the intervals, basically from -infinity up until 4. That's it. -infinity to 4, 4 to infinity. It's got a relative minimum, and that one has no relative extrema because of, and again, just looking at the signs of the first derivative. That's using the first derivative test. Okay. And then we're into our next section. So that's enough for this one. We'll do one more video, 12.2, and we'll be ready. All the tests will be prepared. Thanks.